Welcome back to the lectures in quantum chemistry and molecular spectroscopy. In the past lecture, we saw a few examples of normal vibrations of a linear and nonlinear triatomic molecule. At the end of that lecture, I also mentioned that I would show some examples of normal vibrations as computed using quantum chemical methods and visualized in other polyatomic molecules, many atom polyatomic molecules such as benzene and the methane, ethane and many others. So, this lecture is a visual presentation of some of these normal modes. The classification of them by the approximate nature such as bending, torsional or scissoring or ring puckering, ring torsion, out of plane bending, all these things, I mean they are some things that you have to see the motion and then classify them. Most important to the lecture is that these normal modes have been calculated ab initio using quantum chemical packages, and I use one of the softwares which we use in our classrooms in IIT Madras. The software is Gauss View, which allows us to visualize molecular structure as well as the coordinates of the molecules, and in this particular lecture I show the molecular vibrational modes. Okay. So, the lecture is on polyatomic vibrations, and there are illustrative examples of normal vibrations. We shall see simple polyatomic modes of methane, ethane, benzene, to name a few. Okay. Methane, CH4, it is a 5 atom molecule, nonlinear, it is a tetrahedral structure, it has a tetrahedral structure, and there are 15 minus 6, 9 degrees of freedom. Okay. So, we shall look at the methane molecular structure. Okay. This is a 3-dimensional perspective. I think by now you can see that the tetrahedral structure is clear in this form, and let us also look at the vibrational modes of this molecule. Now, what we have in the small table, you may not be able to read this, but let me give you the gist of it. There are 9 normal vibrations, 1 to 9, calculated according to the harmonic model, namely the harmonic force field model, meaning that the vibrations are of small amplitudes and the frequencies are in centimeter inverse that you see from here, roughly starting from 1413 centimeter inverse to about 3248 centimeter inverse. There are 9 of them, and you can see that this molecule is a very highly symmetric molecule. Tetrahedron is a molecular system which has 24 symmetry elements according to the point group structure of the molecular structure, and the presence of a threefold axis, threefold rotational axis about any carbon hydrogen bond, and there are 4 such threefold axes, introduces degeneracies in the vibrational frequencies. I mentioned this in the last lecture, and so you can see that 3 of the vibrational modes are degenerate with the frequency 1413 centimeter inverse. 2 others have a different frequency of 1624 centimeter inverse, and then 3 others have degeneracy with 3248 centimeter inverse, and these are the stretching modes, the symmetric and antisymmetric stretching modes that you see here, 3111 and the 3248 centimeter inverse. These are the high frequency modes, and these are basically bond stretching vibrations, and all the others are bending and torsional vibrations. Let us see the vibrational motion of the first frequency 1413 centimeter inverse. You can see that this is a bending mode, or you can also call it, let us see how it works. So you can see that this is typical, a pair of the plane of the bend HCH is constantly changing. Now, since you have 4 atoms, you can pick 2 pairs, but then these 2 pairs can be picked in 3 different ways. Therefore, whatever you see here as one pair doing, in the other degree of freedom you will see another pair doing the same thing. You see that it is like 1 2 as one pair, 3 4 as another pair. The motions are some things like this: 1 2 3 4. The motion associated with this is identical to the other pair 1 3 2 4, and it is also the same thing as 1 4 2 3. It is so in this case because all 4 atoms are hydrogen atoms, identical, these 4 hydrogen atoms. Therefore, the motion of these 4 atoms in pairs, there are 3 pairs, and therefore you have 3 frequencies. This is what is called the triple degeneracy. Normal vibrations. Normal, it is a bending mode. Okay. Now, let us go to the other one also. Okay. Let us look at the 1620. Yeah, you can see the 1413, the next one. You see the other 2 pairs do exactly the same degree of same motion. So, look at the 1624 now. This is a very different motion, and this is doubly degenerate. You can see that. So, these are the only 2 different ways by which this particular bending motion can be created. Now, the high frequency vibrational mode 3100 centimeter inverse is what is called the symmetric stretching mode. Let me just show that. Okay. You see if I can see that in some, yeah, I think this is a more clear, this is a clearer perspective view. You can see all the 4 bonds stretch identically, and quite of course methane does not have a dipole moment, and in this motion throughout the motion methane also will not have a dipole moment created at any point of time, because any dipole created in one direction is going to be compensated by the dipoles, the collective dipoles created opposite to that, and therefore this motion is dipole free motion. And you can see the 0 associated with the dipole free essentially means that this cannot be detected by the infrared spectroscopy. Infrared spectrum cannot contain this. This can be detected only using Raman spectroscopy. Okay. This is a symmetric stretch, and then you have anti-symmetric stretch. You can see that you see that 2 of the bonds stretch anti to each other. One bond is shortened while the other bond is lengthened. This clearly introduces dipole moment during the vibration, and the rest of the atoms move to ensure that the center of mass of the molecule does not move away and there is no translation. Therefore, this is a genuine vibration, and since you have a pair of these molecules undergoing the symmetric and antisymmetric, that is stretching and the shortening, while the other pair undergoes the balancing act, Again, this can be 3 different ways of doing it. So, if you call this as 1, 2, if you call the 2 atoms which undergo stretching as 1, 2 and the other as 3, 4, then you will have 1, 2, 3, 4, 1, 3, 2, 4 and 1, 4, 2, 3, and those are the 3 different vibrational frequencies that you can see, and in this case you can see the stretching and the antisymmetric stretching are clearly seen by all the others. Okay. And the third one is in a similar way. Okay. Okay. Therefore, this is an example of the 9 normal modes that can be visualized using a simple 3-dimensional program and a 3-dimensional viewer. Okay. Let us move on to the next molecular system, ethane. CH3, CH3, it is 8 atom molecule and it has 24 minus 6, 18 vibrational modes. This also has the 3-fold axis symmetry. So, this model, this is the vibrational the spectrum of ethane that we will see. Okay. So, in this form you can see the 2 tetrahedrons. Okay. From here, of course, you see what is called the staggered configuration, not the eclipsed configuration. This is a staggered configuration, and you can see that the 2 tetrahedra. There are 18 frequencies which you can see numbered from 1 to 18 here, and ethane also does not have a dipole moment, 0 dipole moment molecule, but some modes of ethane during the vibration will create the dipole and then the dipole will go to 0, dipole moment will go to 0, increase to some value, go to 0 and so on. So, those modes are infrared active, and the other modes which are not infrared active will be Raman active. So, here is the low frequency mode of 330 centimeter inverse. These energies which are calculated from quantum chemistry packages are approximate. There is an error of between 5 to 10% depending on the level of accuracy that you have, the level of approximation that you have. One of the goals of quantum chemistry is to simulate and obtain the vibrational frequencies very, very precisely by including unharmonic motion also. We will not worry about that in this lecture. We want to see qualitative picture of what are called the collective vibrational modes, the normal vibrational modes. So, let us start with the lowest frequency vibrational mode, 331 centimeter inverse. You can see that the rings rotate relative to each other. This is what is called, generally called a torsional motion. Okay. The motion is the rings, the 2, 3, 4, what is this? The 2 fragments, the metal fragments rotate relative to each other. Okay. Let us take the next one, which is a doubly degenerate mode, 850 centimeter inverse. Now, you can see that this is more like the 2 benzene, the 2 metal fragments. The bending motion generally creates a dipole moment in that process, because the dipole moment is probably in this direction and then it goes to 0, in this direction and then it goes to 0. You can see that. And now, the other thing that you have to see, that the motion of carbon atoms, the amplitude of carbon atom vibrational motion, you can see that is much smaller than the amplitude of the vibrational motion of the hydrogen atom, which is also something that I said in the last lecture, that in normal vibrations atoms vibrate with amplitudes which are inversely proportional to the square root of the masses, and you can see that carbon is much heavier, 12 times heavier than the hydrogen atom, and therefore 1 by square root of 12, its amplitude is roughly 1/3 of the, slightly more than 1/3 of the slightly less than 1/3 of the amplitudes of vibration of the hydrogen atom or the bending motion. The other motion 843 is basically the other plane. It is in the other plane perpendicular to that plane. Okay. Now, let us see the next degree, next motion, namely 1049. Very easy. It is a symmetric, but it is a carbon-carbon stretch, CC bond stretch. No dipole, because the dipole moment is 0 throughout in this process. The dipole created by this carbon-carbon bond is cancelled by the dipole created by this carbon-carbon bond, and therefore the other things do not move. Go to this 1270. Let us see. So, this is again bending involving as well as the carbon and the hydrogen atoms. There are two such motions, both are degenerate. So, you can see that it is in the other plane, you can see that. The next vibrational mode is the 1464 centimeter inverse. The methyl groups, if you look at it, if you look at these methyl groups, they are opening and closing like the umbrella will close. For example, this is closing of the umbrella while this is opening up, and you can see that they are in the opposite directions, and therefore there is a net dipole moment created during the motion, and then it goes to 0. And again, the amplitudes of carbon are much less relative to the amplitudes of the bending hydrogen atoms, and this has a large dipole moment, and therefore this can be detected by the infrared spectroscopy techniques. Then let us go to the next one, 1491 centimeter inverse. This is also very similar. Let us see. No, here they are opposite, sorry. It is not similar. The one umbrella closes while the other umbrella opens. You see that as this goes up, this also goes up. Therefore, wait, no, as one umbrella closes, this also closes. Therefore, these two modes cancel each other. So, there is no dipole moment in this process. Yeah, the motions are opposite each other. Therefore, this is the bending motion like the umbrella inversion. 1568, you can see that it is also doubly degenerate modes. So, what is happening here? Let us see. Yeah, you can see the motion of the two hydrogen atoms relative to the in the opposite extent moving. This is another normal mode. Let us go to the more energetic one, the bond stretching and the symmetric and antisymmetric stretching. Okay. This is the anti-symmetric stretching of the carbon hydrogen bonds. Okay. You can see that one bond stretches while the other bond shortens. What about this? Yeah, this is also antisymmetric stretching. And then you will have a no, this is also two of the bonds are shortened while the other bond is lengthened. So, this is also antisymmetric stretch. Okay. So, There is no symmetric stretch here. Ah, there is, okay. All the three are symmetrically stretched. You can see that. All these three are symmetrically stretched, while all these three are also symmetrically stretched, and that frequency is 3112 centimeter inverse, and you can see that these stretches are in the opposite direction for this one and this one. Therefore, there is a net dipole moment, as a result of which this mode is also infrared active. Okay. This is for ethane. Let us go to the last example of this lecture, namely benzene. C6H6, most important organic molecule, among the most important organic molecules. 12 atoms, a planar molecular configuration with all the hydrogen atoms in the hexagon, symmetric, perfect hexagon. This is not, but the molecule is a perfect hexagon, and so 12 atoms, there are 30 vibrational modes. Very beautiful paper in the early 30s by Professor E. Bright Wilson Jr. in Harvard University. He is also credited with having guided many students. More than 10 or 15 of his students have won Nobel Prizes in chemistry for their contributions in many different areas. He was one of the best known vibrational spectroscopists, and Wilson and Howard produced the most important simplification on the molecular rotational vibrational Hamiltonian in 1936. So, it is a very well known name. Bright Wilson Jr. studied the normal vibrations of benzene. And provided some classifications on the symmetry classifications of these benzene. Benzene is it belongs to the molecular point group. When you study group theory, you will see this belongs to a point group known as D6H. It has a 6-fold axis of symmetry, very highly symmetric system, and therefore many of its vibrational modes are also degenerate. Let us look at the vibrational frequencies here. So, there are 30 vibrational modes, as you can see, 1 to 30, and the lowest vibrational frequency is 414 centimeter inverse. And what it does, okay, it is not seen from here. When you rotate, you can see how the planarity of benzene is lost. So, this is the motion that destroys the planar structure of benzene due to the vibrational motion of the carbon atom, the two carbon atoms in and out of the plane, and the carbon, of course, as a CH entity moves. This CH entity and the CH entity move in such a way that the rest of the frame moves in the opposite direction. There is no dipole created in this process, and this is not infrared active. The other 414 is now the ring, whatever that was not moving very fast, now it is moving in that direction with the CH fragments moving very slowly. Compare this with that, you see that. So, this is one in plane out of plane bend, and this is the other in plane out of plane motion. Okay. Then there is the next one at 621 centimeter inverse. Wow, the ring is distorted. It is no longer a symmetric 6-fold ring, but it stretches and then comes back to equilibrium. It is also a motion such that there is no dipole produced, because you can see for any one particular motion, for example, of this fragment, the opposite fragment on the other side moves in the opposite direction. You can see that if this goes away, this goes in, and if this moves away, this moves in, so that there is no net dipole moment. The next one is, of course, it's a similar motion, except that this is about the other plane. You can see this is about one plane, one set of axes, and this is about the other. Then you have a very large infrared active mode, 693 centimeter inverse. You can see that the whole of all the 6 hydrogen atoms move out of plane, and their amplitudes is much higher, much larger than the amplitude of the benzene ring, all the carbon rings, which move very slowly to compensate. The center of mass remains exactly where it is throughout the motion. But in this mode, of course, a dipole is created significantly during the motion, because if all the 6 hydrogen atoms move in one direction, a dipole is created along this axis, and then it goes to 0 and so on. So you see that this is infrared active. It's easy, you have to rotate to see the perspective view of these normal modes. Okay. Then there is this 717 centimeter inverse, in which you can see that a group, this entire group of CH, this whole moves in one, this is in one direction, this is in the opposite, and then likewise for the other. I mean, all of these motion destroy the symmetry of the plane of benzene. However, the dipole moment is not there. 863 centimeter inverse, there are several of them, there are 2 of them, and you can see that one, it's the pair of hydrogen, one set of hydrogen atoms, and it's the other in the other motion. So let's go to the last example of this, namely the 3215 centimeter inverse. The whole ring is breathing in and breathing out. This is symmetric stretch of all the 6 hydrogen atoms, identical extent, and the ring closes in just to ensure that there is no translational motion. So this is the most symmetric of the normal modes, and this mode obviously has the highest symmetry, that it's not changed by any of the symmetry operations that you can perform on the benzene ring. The antisymmetric stretch is given by this 3200 centimeter inverse. You can see that, yeah, this is antisymmetric. The 2 hydrogen atoms, when they stretch, these 2 hydrogen atoms close in and opposite, and you can obviously have one more mode in which the similar thing happens with the other hydrogen atoms. And these modes are highly infrared active. The 3188 centimeter inverse, it is also antisymmetric stretch, but please note that this does not produce any dipole moment. Freeze it for a moment, see that the atoms are moving in the opposite directions, and therefore you see that there is no dipole in this process. This is the ring is, I don't know whether it's called the puckered, ring puckering motion, or it's definitely the distortion of the ring in a very, very serious way. It's approximately half the frequency of the completely symmetric stretch frequency. Now, there are hundreds of molecules, there are thousands of molecules, probably tens of thousands of molecules that people have explored using this program called the Gaussian, and enables us to calculate many molecular properties from ab initio quantum chemistry, and vibrational motion can also be studied more carefully using some of the more accurate components of the Gaussian program. The purpose of this lecture is to visually illustrate that there are what are called the collective motions of the atoms in the form of normal modes, and that these normal modes follow an exact mathematical description that we are familiar from classical mechanics, and it's possible for us to measure these things experimentally and correlate molecular degrees of freedom with the properties, whether they are infrared active, whether they are Raman active, whether one can study the bond length and bond angles, which the torsional angles, and therefore whether there are internal potentials for molecule fragments rotating relative to each other and so on. So a whole lot of molecular properties can be understood using vibrational spectroscopy. However, we have to come to a close on this topic for this course. The next 2 or 3 lectures will be on molecular rotations, and we will look at microwave spectroscopy of a simple diatomic molecule, followed by a few symmetric top molecules. With that, we will come to an end of this course. Until the next lecture on rotation spectroscopy starts, thank you very much.